My name is Emir. I'm gonna introduce you to proof writing techniques, and in particular, and probably we're gonna walk through some problems individually. And this is an introductory course to the playlist of my YouTube channel, which introduces you to how to actually write proofs and learn mathematics in the right way. Now, this handout is available in the links prescribed, and you may attempt some of the problems and maybe try to do something else and ask questions. We're free to open in the comment section. So, okay. Now, let's go through the introduction in this talk. Okay, so introduction to formal proofs. Sometimes you're given a statement that is directly proven through some algebraic or analytical skills, which just implies some logic. For example, let's say P and Q are logical axioms. P implies Q, meaning that there's a direct manipulation of an instance, such as let's assume that 2 minus 2 is equal to 0. We know this is true since 2 minus 2 is actually equal to 0. This is a direct implication. Now, for more examples, there are some cases where you have to actually apply those rules, and sometimes it might be a little tricky, and it's the base of all proofs. Now let's say by theorem 1, let's define a trace, the sum of diagonal integers of a matrix, meaning that for matrix A prescribed here, the diagonal sum of the matrix it would be A11, A22, and A33, the sum of those three terms. For B1 is the same. Now we need to prove that the trace of A plus B there is directly proportionate to trace of A plus trace of B. We can actually sketch the proof, or we can prescribe it. So we define a matrix A with interest like this, and a matrix B with interest like this. Then we compute the sum of those matrices, and we notice that A11 plus B11 in the linear combination of those variables is actually equal to our trace, which can be described well by using the associative and additive properties of a matrix that we can use for summation variables. It's actually not that hard to prove that this is our true variable of an instance. Now we computed our x-values, and we're probably using it intuitively sometimes. When you're giving in a really interesting, really easy problem, you can just manipulate it and actually prove that this by some theorem is true. Now, another thing I want to talk about is the well-ordering principle. The well-ordering principle, what it tells us is, if we're given a set of a subset of real numbers, there should be a minimal value that at least I know what. For example, for the natural numbers is 1. Natural numbers are in the form of 1. Natural numbers are in the form of 1, 2, 3, and 4, and so on. So the minimal value here is 1. The same applies for any non-empty subset of z plus natural variables, since the implication of a plus, since when you go to the negative, there are actually no axioms to support this variable. Now, another thing I want to talk about is proof by contradiction. Now, what is generally a proof by contradiction? A proof by contradiction is if we assume that some statement is given, we assume that there's an implication of a non-statement for the statement. If we can prove that the non-statement is actually false rather than true, then we can arrive at a contradiction, meaning that we do imply this variable. Let's say, let P and Q be logical expressions defined by the implication of P implies Q. To prove that some variable statement, if not P implies Q, then we prove the assumption is wrong by some proper logic. Hence, we provide an explanation for the implication of P to Q. This is the proof is trivial. There's no one proof. It's a rightful technique for all instances. Now, let's look at the handout. The proof by contradiction is really useful since there are lots of arbitrary values that come here. So let's provide a theorem. We already derived the formula, the definition for the proof of contradiction. Now let's look at the following example. No smallest positive rational number. So what are rational numbers in general? Rational numbers are in the form of some real numbers a such that rational numbers are in the form such that for natural numbers or non-natural numbers in general, we can actually prove that they're in the form of a and b for a and b in the set of natural numbers. Set of natural numbers. If you can derive it from here. Now, let's assume false. Let's say there is a smallest positive number. By our logical expression, we assume that the first statement is false. Then let's say derive it to r, but r divided by 2 is also a positive rational number. But clearly r2 is less than r, hence a contradiction. Well, this is an implication for all rational integers. It's also for all positive rational numbers. There is a minimum value for all negative rational numbers. Then this variable is left as an exercise for the reader, or should I say the watch. So now let's go through mathematical induction. Okay, so this is the common proof technique for all the statements below that is going to be prescribed here. So principle of mathematical induction. We say that to prove a statement P for all integers in the form of at least of n0, meaning that n0 by well-ordering principle is the minimal value. We begin by proving P of n, which is P is just a statement. So P of n should be the minimal value that should prove that this equals this, the arbitrary function is true. If there's an implication that P of n, we're going to assume that P of n is true. If you can provide a proof that Pn plus 1 is also true, then it's true for all rational numbers. Since what an induction principles do is like a tillings. Once you have a tilling, one proves the other. Since if we can prove for the minimal value, then we can prove for all natural rational integers since they have a difference in 1. Okay. The proof is trivial. By the well-ordering principle, the minimal value here ends here. Now, for the handout, the induction principle is actually derived two separate times: general induction and strong induction. So what a strong induction does is we prove, instead of proving that for the minimal value, you prove that every particular value from in the form of p0 implies pq plus 1. Yeah, here's the derivation of the general induction principle. Now, for let's say the sum of for first n natural numbers, for all we have that we have here. So our base case, or should I call it n0, is that we derive at 1. If you plug in this equation to 1, then 1 times 2 divided by 2 is just 1. So the base case holds. Now for the inductive steps, we assume that it's true for some k plus 1. Then it's derived from here, and from k, and we can prove it by k plus 1 by plugging in the sequence here as prescribed below, and if we can prove that this actually equals k plus 1 plus k plus 2, then the formula holds for all natural numbers. Now let's look at the following examples. And the strong induction principle: let Pn be a proposition divided by n if base case is true, inductive state for all k less than the greater or equal to n0. If Pn0 and Pn0 plus 1 or for k are true, then pk plus 1 is also true, meaning that we imply for all the particular variables that pk plus 1 can be true for all. It's sometimes also referred as real induction principle, since it also derives some variables instead of other congruent holdings in the sort. Yeah, sorry, English is not my first language, so there's some instances where I'm gonna present something as it is, and you may comment on my bad English if you want to. Now, okay. Now let's go through it. So, okay, it's a 2-page variable, right? Now, okay, let's say our example is here. Every integer in the form of n is greater than 2 is a product of primes. Okay, now for every integer n plus equals can be described as a product of one model primes. Let's say for base case 2 is the product of primes, since 2 is prime itself. The inductive statement assumes that every integer m is set of 2 is less than m and k. If we can prove that for all instances such that they're less than or equal to k, then the inductive statement is done. So we should prove that k plus 1 is actually written in the form of primes. If k plus 1 is prime, then done. But if k plus 1 is composite, there's a proper divisor a. But since we have that b is, let's say b called b, ab, so then one of them is going to be a prime, can be also written by product of primes, then this should come to the implication that is also a product of primes. This is done by strong induction, and every n plus 1, 2 is done by product of primes. There's some instances where you can actually apply this rule. We're gonna look at them later. Let me just. Okay, now let's look at some general problems. The first 10 problems are just introductory, and if you want to challenge yourself, you can do the last 14 or 12. I don't know. So let's say prove that root over 2 is irrational. Well, this is easily done, since if you assume this rational, then it's in the form of AB. Let's call it irreducible. Then if you know that if it's irreducible, we can prove that the square of those numbers is actually not irreducible, meaning that it can be reduced to its smallest terms. Hence, we arrive at a contradiction. Oh, look, a famous problem, number 2 is a famous problem. Prove that there is an infinite many prime numbers. This comes from the Euclid lemma of infinitely many prime numbers. So let's have a look at this. So if we have infinitely many prime numbers such that in the form of Pn plus 1 and 1, 1, if we can prove that if this variable plus 1 is actually, if there's a prime number that doesn't really divide us, then we can prove that n is also a prime number, meaning that the assumption is actually wrong. No smallest integer positive rational number. This is just done by the exercise. You can just do it as an exercise, you too. Yeah, this one is interesting. So modulus 4 is mean that is the remainder of 4. This is trivially done, since n squared is in the form of 2k or 2k plus 1, and 2k plus 1 is 4k squared plus 4k plus 1, which only derives one modulus. So there is no square number such that it has the variable, it has remainder 2 divided by modulus 4. Yeah, this can be also done by contradiction. Now this is a trivial exercise. It's actually really easy when you want to apply it. Now let's go with our divisibility. So when it comes to divisibility, we can actually prove that for k, a rational number k, we can minus the k, and if this actually has an axiom of divides by 7, then we prove that the previous term is also divided by 7, meaning that it's also derived as a induction. Yeah, and then it's finally done, right? Yeah, so this is a triangle inequality, I think. No, it's okay, no. So some of the some hard problems are left as an exercise, although I think I'm gonna walk through. These problems are all induction. The first problem from Putnam 2004, sorry. So we derive at the sequence. So determinant is just un plus ab minus cd, meaning that if this a, b, c, d. This should be really trivial. I think my best advice for you is just look at the first samples and just guess the structure. By guessing the structure, you can really arrive at a sequence or a sequence, or the inductive step. You can actually implement it. This is not primarily induction, it's more of linear algebra, but I think you can do it, yeah. There's not much linear algebra involved here. Well, this is from the recent Asia Pacific Mathematical Olympiad. this is a really easy induction problem. I would say not really easy though. It takes a lot of steps to actually prove this, but it's actually really trivial for our base cases, so you don't have to really worry about it. Yeah, these are just some combinatorial problems. If you're struggling with combinatorial problems, you can actually skip those and do the only ones that involve induction in some sort. Okay, now some IMO problems too. IMO P6. These problems are actually somewhat hard for some people, or generally hard. But this is really done by strong induction. If you could, if you can prove this by strong induction, then you're practically done. So yeah, thank you for watching. This has been a wonderful experience for me. It's my first video, so I would accept hate maybe, because I need some advice for my future videos. Thank you for your time and effort. I hope this has helped you a lot. I'm gonna give links to all of the handouts or prescriptions, some problems to you. So bye. Yeah.